Okay, so welcome back to this video in which we are studying the pore of the nicotinic acetylcholine receptor. So we've seen how the pore of the nicotinic acetylcholine receptor is lined by these 5 M2 membrane-spanning alpha helices. Okay, so now what I want to talk to you about is how within the pore of the nicotinic acetylcholine receptor you are going to have these rings of negative charge. Okay, so let me just discuss this a little bit more with you. So if we now see the pore from the side aspect, okay, so if I draw the pore like this from the side aspect, so here is a cut-through portion of a M2 alpha helice, and here's another one. So basically what I'm doing is I'm cutting down maybe through there, okay? And we are looking now at it from the side, okay? So here is the phospholipid bilayer maybe. Well, actually, well, you can say it is if you like, but I was just thinking of these as the M2 alpha helices, but now if I've shown the phospholipid bilayer, I'll have to think of these as the actual whole sides of the receptor. So now we'll have to denote the M2 alpha helice as just this bit here. Right, okay, so we've already discussed how you have these leucine amino acids coming off at this 9' region of the M2 alpha helix, okay, and these form this hydrophobic patch or the hydrophobic girdle which occludes the channel and stops ions from being able to move through it because the leucines are all very hydrophobic and neutral and don't interact very favorably with ions, okay. But you're also going to have rings up here, and you're going to have another ring down here, and finally another ring down here. So you're going to have basically amino acids conserved at certain portions of these M2 alpha helices so that you get rings of 5 amino acids that surround the pore, okay? So these rings basically have negatively charged amino acids on them, and these rings are believed to help the positively charged ions, the cations, such as the sodium cation and the potassium cation, to move through this channel. So this ring of leucines that we've got down here at the 9' position, this is the gate, basically. This is what's stopping ions from moving through when the channel is in its closed state. But we'll move this out of the way when the acetylcholine binds, and then we want ions to be able to move through. Specifically, we want positive ions and not negative ions to move through. So what we have are these rings of amino acids lining the pore, rings of 5 amino acids, one provided by each M2 alpha helix, which are going to line the pore and support the movement of positively charged ions through, because they'll be able to interact with the negatively charged amino acids that lie in the pore. So you have one above the leucine ring, i.e. you have one extracellular negatively charged ring here, and then you have 2 lower ones down here, okay? So this one is known as the extracellular ring, so this is the extracellular ring of negative charge, okay, so this is the extracellular ring. Then the one in the middle is known as the intermediate ring, so this is the intermediate ring, and then the one towards the cytoplasmic side is then known as the intracellular ring, so this is the intermediate ring, and then finally you also have an intracellular ring down there. Okay, right. So, which amino acids then do you have in these 3 rings that are going to contribute this negative charge? Well, in the extracellular ring, there are 3 amino acids that you can have in this 20' position. And by the way, the extracellular ring is formed by 5 amino acids which form this ring, and these amino acids are at the 20' position. So above the 9' position towards the extracellular aspect, you'll then have this ring. So if I draw these other 2 M2, well, these other 5, other 4 M2 alpha helices I should try to draw, but I can't really do that without making the picture look bad. So I'll draw 2 of them at least. So now I've got 3 M2 alpha helices on there, and basically again at position 20 prime, you'll have a negatively charged amino acid, so you'll end up with this ring of 5 of them. So what amino acids can you put in this 20 prime position? Well, it's not one set amino acid. Okay, so the one that is most common for most nicotinic acetylcholine receptor subunits to use is glutamate. So let me show you the structure of glutamate. So, glutamate, or glutamic acid, but what we're hoping is that it will be glutamate, and I'll talk you through the difference between glutamate and glutamic acid. So, here is the amino acid residue. So this is the core structure at the moment. And then the R group of glutamate is that you have 2 methylene groups. So here's the first methylene group. Then you have another methylene group here. Okay, and then finally you have a carboxylic acid group on the end here. Okay, so this is the structure of glutamic acid. So glutamic acid. Okay, and glutamic acid has the 3-letter amino acid code GLU, G-L-U, and the single-letter amino acid code E. It can't have the single-letter amino acid code G because G went to the amino acid glycine. Okay, so this is glutamic acid. Now, what's glutamate? Well, basically, glutamic acid is an acid, funnily enough, okay, and that means that it can donate protons. Okay, so what can happen is this hydroxyl group here, this alcohol group, can donate that proton away. So let me show you this carboxylic acid group in a bit more detail. So, this bond between the oxygen and the hydrogen is a covalent bond, and the hydrogen gives 1 electron and the oxygen gives the other. Okay, now what can happen is this bond can cleave basically by heterolytic bond fission. So it's going to cleave by heterolytic bond fission. Now, heterolytic bond fission means that the way that you break the bond is uneven basically. When you break this single bond, both of the electrons are going to go to one chemical species, so they're both going to go to the oxygen, and the hydrogen is going to get nothing. That's in contrast to homolytic bond fission, where you basically evenly distribute the electrons. One electron goes to the oxygen, the other goes to the hydrogen. So we're going to heterolytically cleave this bond, and basically both electrons are going to go to the oxygen, and that's just going to leave the hydrogen as a nucleus, because hydrogen only has 1 electron, which is now lost. So you're just going to be left with a hydrogen nucleus. Now, the hydrogen nucleus usually just consists of 1 proton. I mean, there are other isotopes of hydrogen, but the most common isotope of hydrogen, you just have 1 proton at the center. That's the protium isotope. There are other isotopes such as deuterium and tritium, where you have 1 neutron in addition to the 1 proton in the case of deuterium, and 2 proton and 2 neutrons in the case of tritium. But the most common form is protium, which just has no neutrons and just 1 proton. Okay, so whichever isotope of hydrogen it is, it's going to go off with a positive charge. Okay, and we'll assume this is just a proton. Right, so it's donated this proton away, and that then leaves what behind? Basically, this hydrogen has gone now, so we'll separate that off, okay, and now this oxygen is left with a negative charge. Now, the molecule that you are left with after the hydrogen has gone off, after the proton has cleaved off by heterolytic bond fission, the amino acid residue that you're left with will have this carboxylic acid, which is deprotonated, okay, with this negative charge like so. That is known as the conjugate base of glutamic acid. And it also has another name. Its other name is glutamate. So glutamate is the conjugate base of glutamic acid. That's the strict difference between glutamate and glutamic acid. Glutamate is the molecule once it's lost its proton. Glutamic acid is the molecule when it's still got its proton. Okay, so glutamate will have a negative charge. Glutamic acid is neutral. Okay, so the important thing to understand is that if you put glutamic acids in these 20' positions, what will happen? some of them will donate their protons away and become the conjugate base. And it's called the conjugate base because this new structure over here, it has a negative charge, and it's certainly not an acid. It can't donate protons anymore. What's left is certainly not an acid. Instead, it's a base because it can actually receive protons. You can stick a proton onto that negatively charged oxygen. So the conjugate base of glutamic acid is actually a base. So there's always that kind of irony with acids and bases, that they're kind of the two sides, the two faces of the same coin, okay? So there's the protonated form, which is the acid, and the unprotonated form, which then becomes a base. So when you actually do what an acid does, you become a base in that process. Okay, so that's the difference between glutamic acid and glutamate. It also explains why having this amino acid at position 20 is going to lead to having a negatively charged residue there, and why that's going to be helpful with regards to conducting cations through the pore. Okay, so glutamic acid is just one of the amino acid residues that you can have at position 20. You can also have aspartic acid, which is a very similar structure. So if I show you aspartic acid, and again, the strict difference between aspartic acid and aspartate is the same as the strict difference between glutamic acid and glutamate. So let me show you now the structure of aspartic acid. So aspartic acid is glutamic acid with one less methylene group. So you hopefully can see the difference. We've taken one of these out. Okay, so this is aspartic acid, okay, which has the 3-letter amino acid code ASP and the single-letter amino acid code D. Again, it cannot have A because A went to alanine. Okay, right. So aspartic acid, again, is an acid because it can donate this proton away, and when it does donate that proton away, it becomes the conjugate base of aspartic acid. It becomes negatively charged, and the conjugate base of aspartic acid is what's known as aspartate. Okay, so the conjugate base is equal to aspartate. So it's really the aspartate residue that you want in position 20, because it's the aspartate residue that has the negative charge. So you can either put glutamic acid or aspartic acid. There is one final one that you can have in position 20. So let's go over the page to discuss this final amino acid that you can put in position 20. So the final amino acid that can go in position 20 is the amino acid glutamine. So let me show you this. Glutamine has a similar structure to glutamate, except that it's the primary amide of glutamate. Okay, so again it has these 2 methylene groups, and then here's the carbonyl group, but now it's not in a carboxylic acid group. Instead, it's in a primary amide group. So instead of having the alcohol group, it has an amino group of that carboxylic acid carbon. Okay, so this is the glutamine molecule. Okay, and the 3-letter amino acid code for glutamine is GLN, and the single-letter amino acid code for glutamine is Q. Again, it couldn't be G because of glycine having G. Right, okay, so why is this negatively charged? Well, this one is only a partial negative charge this time. So you'll notice that this oxygen and this nitrogen here, those both have much higher electronegativities than the carbon. Okay, so the electrons in this single bond and this double bond are going to feel greater pulls towards the oxygen nucleus and the nitrogen nucleus than they will towards the carbon nucleus. So basically this makes the nitrogen partially negatively charged, the oxygen partially negatively charged, and the carbon partially positively charged. So the tip, these 2 structures here of the glutamine amino acid will be negatively charged, and that's why you can use this also in position 20. So in summary then, position 20 of our M2 membrane spanning alpha helix is going to have either glutamic acid or glutamate, which is E, or it's going to have aspartic acid, D, or it's going to have glutamine, Q. So it can have EDQ there, okay? So this is going to give us a ring of negatively charged amino acids. which will assist the ions moving through this channel once we've actually opened the hydrophobic girdle. Now you've got more of these rings of negatively charged residues. You've got the intermediate ring and the intracellular ring as well. Now which residues on this M2 membrane spanning alpha helix do these correspond to? Well, the intermediate ring corresponds to the amino acid 0', which I told you in a previous video does actually somewhat face onto the loop. Okay, so let's highlight the intermediate ring in green. So you'll have 5 of these 0 residues poking into the ring, and you'll form this ring of them all around. So let's put the other 2 there. Okay, so you've got these 5 0 residues. Now what can you put at position 0? Well, it's always set. You put a glutamic acid there. So you've got this ring of glutamate lining the pore there. And these are all, well, some of them at least, are going to lose their proton and become glutamate, which has a negative charge, and this will assist the positively charged ions through the pore. Okay, and this intracellular ring of all 3 of the negative charged rings in this pore, this intermediate ring is the most important for helping the cations through. And the final ring, this intracellular ring, is a residue that's down here, not on the alpha helix at all anymore, it's down here. And this is the the minus 5' residue down here. Okay, so again, you'll have these 4 minus 5' residues which mark, surround the pore very low down. So this is a ring of negatively charged amino acids right at the base of the pore, nearly once you're in the cytoplasmic side. Okay, so this is this ring right down here. And these amino acids in these minus 5' positions, these can be either aspartic acid or glutamic acid residues. So again, negatively charged residues, at least once they lose their proton. So you have these 3 rings of 5 amino acids which surround the lumen of the pore, and they have negative charge, so they assist the positively charged cations moving through the pore when the pore opens, i.e. the hydrophobic girdle allows ions to move through in response to acetylcholine binding. Okay, in the next video what we'll discuss is the open channel blockers of nicotinic acetylcholine receptors, and we'll also discuss the SCAM technique. Okay, see you in the next video.